Good morning. Welcome to our webinar this morning. This morning we're going to be looking at a comparison of Bürkert's pneumatic modulating control valve technology versus our Electromotive actuation technology. The agenda for today, we're going to start by looking at the element actuator technology. So this is Bürkert's pneumatic modulating control solution. We launched that about 25 years ago, now onto the market, and is one of the most accurate, fastest acting modulating control valves that is currently available. Following that, we're going to have a look at our EVA technology. So this is our Electromotive actuator technology. And this is moving things on to a new level. Following looking at the details of both actuators technologies, we're going to do a live demonstration, hopefully, where we're going to give both valves a control signal and see how they react to that control signal. Following that, we will have a head-to-head, so we will see how both of our technologies compare to the other, and then we will end the session this morning with a question and answer session. So any questions that you might have, we will of course be happy to answer them at the end. A little bit on myself, first of all. My name's Kieran Bennett. I'm the Business Development Manager for Food and Beverage for Bürkert UK. I've been with Bürkert UK now just over 14 years. I'm a specialist in steam systems, dairy applications, modulating control and rotary valves. I also have other areas of responsibility, such as in the chemical and petrochemical industry, as well as responsibility for the whole hygienic industry, including pharma and biotech, with my colleague Damien Moran, based over in Ireland. When we look at Bürkert's modulating valve portfolio, we build things up in a modular fashion. So we have a range of different body styles, everything from the angle seat to the full hygienic diaphragm valve, the actuator technologies, and then automation that would fit on the top of those if required. But for the purposes of today's webinar, we're going to be looking at the element pneumatic solution and the EVA Electromotive solution. So, starting with element, Bürkert's pneumatic solution. When we launched this, it was designed to be an aesthetically pleasing stainless steel valve solution, beautifully engineered, but with the best performance available. So starting with the beauty and the external side of things, it is IP rated to IP65 or IP67. That is dependent on the type of electrical connections that are specified. We try to make it consistent and high class look, so we see a lot of times, certainly in the hygienic industry, where you have a lot of stainless steel vessels, stainless steel pipework, then a cast steel, or even worse, a cast iron valve is specified that quickly, depending on ambient conditions, can start to corrode and look unattractive. Our actuators were designed to E-hedge guidelines for both materials compatibility, the smooth surfaces and the external seals, to ensure that anything that is in the atmosphere, be that moisture, chemicals, are going to be able to not affect the performance of the valve. So A, they can't get into the workings, but also the valve can easily be cleaned and hygienic externally. And durable against cleaning agents for enabling that cleaning. When something does get on it, it needs to be able to be cleaned off so it's safe for personnel around the valve. And then we go to the insides, and for such a simple looking device, we have a huge amount going on the inside. We have outstanding controllability with, in a very, very compact form factor. Not many people are aware, one of the reasons that we have such good ingress protection and long lifetimes of our products, certainly on the pneumatics, is that we overpressurize. We use some of the pneumatic pilot air to overpressurize the electronics at the top here using the pilot solenoid. Those of you who've already used Bürkert control valves will know that we have a cap on the top, and this is a fully sealed unit. And that's so that we can slightly overpressurize these electronics and ensure that we don't have any moisture ingress in and around those electronics that could cause them to fail. And although I'll go through this in a little bit more detail later, we have our compressed air recycling, which now on the actuator side of things stops again that same moisture or chemicals being able to get into the actuator and corrode it from the inside. Typically, on any pneumatic solution, the main point of failure is spring corrosion, and that spring corrosion occurs because in and around the spring, you have moisture from the atmosphere is allowed to enter the actuator itself. With Bürkert's element technology, remove that entirely. So a little bit of a closer look at the core components of the element actuator. Right on the very top of it, we have our jeweled visual position indicator. This is the clear cap on the top. That alongside the yellow puck over the top of the stem means that from 360 degrees around the actuator, you get a clear position indication of what that valve is doing, should you not have a positioner or a control head on the top of it. Our pilot air ports are mounted right on the top. And again, the importance of that will come clear as we move through this webinar. An optimized piston seal around the piston. So we use a piston design rather than the conventional diaphragm actuators you'll see a lot of our competition using. And we optimize that seal to be as frictionless as possible. Friction within a modulating control valve is what would give you hysteresis, so lack of control or difficulty to control the position accurately. We optimize this. The job of that piston seal is obviously to seal the compressed air into the chamber where it's supposed to be. But alongside that sealing, we need it to be as frictionless as possible as that piston moves up and down in the spring chamber. The precision spring to balance against the air pressure so that we can give that accuracy of control. And again, this is the bit that we are trying to protect with our air recycling technology. The internal pilot air ducts, which mean that we can get the pilot air from our top connections down to the bottom, and enables, again, our air recycling technology that I'll go into in a little bit more detail shortly. The spindle, we have a ball burnish spindle alongside the piston seal. That spindle needs to go through the stem sealing pack, and we need that as well to be as frictionless as possible. It's that lack of friction, but that high sealing ability that gives our valves the excellent controllability. And then it's all encased in its hygienic stainless steel housing, which gives the element actuators their sleek stainless steel look. Excuse me. When we start having a look in a little bit more detail, so we're now looking at when we look to put a positioner or control head onto one of the element actuators. You will see, if you take one eye off, that they have the matching integrated pilot air tubes that come down out of the top of the positioner or control head and mate up with those pilot air connections on the top of the actuator. In between the two, we put a rubber seal. This is, of course, installed from the factory if you have the valve as a complete assembly from us, or if you order it as a kit, that comes with the adapter kit that you can see in the middle of here. This means that we have a direct pneumatic air connection excuse me, to the bottom of the actuator, but most importantly, to maintain the aesthetics and the cleanliness externally of our process valves, we have no external tubing. Everything is done internally. We then have a air supply filter. So because we supply these as a sealed unit, that has to be easy to service, so it's externally serviceable. And we have that filter to ensure pilot valve operation. We don't want dirt, debris going through and blocking the relatively small orifices that we have in our pilot valves. It also stops that dirt and debris getting into the actuator as well and damaging the seals there that could lead to premature failure. And finally, we have a pressure relief valve built in. So because we use a piston design, we can actually cope with some of the highest air pressures available, typically up to 7 or 8 bar. And this is normally the kind of distribution pressure of pneumatics anyway. So unlike some of our competitors using diaphragm actuators, which can only be used on relatively low air pressures and would require the use of a separate filter regulator set to regulate down to the required pressure by the actuator, ours typically don't require an additional pressure regulator, which again leads to cost savings for you, the customer. Now, this next slide, although a little bit dated, it goes back to when we first launched the Elements range, is still one of the best ways we actually have for explaining the air recycling technology that we have built into our element valves when they are fitted with either a control head or a positioner. So we're going to start with this drawing over on the left, and on this one on the left, although it's not massively clear, we have the piston in the raised position. So the valve has already been actuated, and in this scenario, the valve would be open. And what we have done now is we have de-energized the solenoid valve, and it has now connected our pressure side of the actuator to the exhaust port. We can see the 3-2 valve now is now connected. Once this happens, we start to vent that air out of the actuator and out of the exhaust port. This is nothing new. The piston starts to move down, and the space around the spring starts to increase. So we need to replenish that space with air. Now, most of our competitors use this and have that connected directly to the exhaust port. And that means that atmospheric air can be sucked in. But with the use of our solenoid valve technology, we recycle the air that has been used to pressurize the valve into the spring changer. And because the pressure of this air is higher than atmospheric pressure, we only get flow of pneumatic pilot air into and around the spring. And then when we want to energize the valve again, we energize the 3-2 solenoid valve, that changes position, and we now allow pilot air from our supply back into the valve, and the piston moves back up, compressing the spring, and we force that pneumatic air out. Because we have now this route blocked, the air can only go in one direction, and that's out of the valve. So we only ever have airflow out of the exhaust port, never backwards through that exhaust port. And although we would never recommend it, as I've already mentioned, our valves are rated ingress protection to IP65 or 67, depending on the electrical connectors. We have often felt that those IP ratings were rather on the low side. So we decided to put our valves to the test several years ago. And we immersed them fully in water, which according to the IP ratings, they should only be able to withstand for around 30 minutes or so. Now we were expecting probably to get a week, maybe a couple of weeks out of it before we start to see some potential water ingress. In actual fact, we got tired out of cleaning the green algae because we were constantly passing air through these valves after around 9 months, and we decided that if these valves could survive 9 months completely submerged, they are going to survive pretty much the most demanding cleaning regimes or atmospheric conditions where we would expect these valves to be installed. Several years ago, we did actually supply just these valves to a customer who was looking to use them fully submerged. Our understanding, they are now at the base of the water fountains out in Dubai, and have been quite happily been running like that for several years. But moving on, one of The big advantage as well we have with our technology is its compactness and its lightweight. So like for like against one of our competitors' valves, and certainly using some of our compact 50mm actuators, we can actually have a combined valve weight of less than half of a conventional diaphragm actuator with a yoke mounted design. But even our standard solution using the 70mm diameter actuator still offers a significant weight and size advantage, which is makes it easier to install, easier to maintain, and a lot of other benefits as well. And we say, which certainly in the hygienic market, which would you rather prefer? Bürkert only manufactures our valves from stainless steel. The actuators are typically plastic with a stainless steel sleeve around them. But this means that because we focus on these materials, we can compete typically with our competitors who are manufacturing their products from cast steel and then painting it to look aesthetically pleasing. But after a few years, that paint can wear away, corrode, and we say, after a few years worth of use, which valve there would you rather have in your dairy, brewery, distillery, or pharmaceutical plant? Many ways to the same goal. We can do exactly the same job as you're about to see using our element valve technology. But moving on, we're now going to have a look at the basics of our EVA electromotive actuator technology. So our Electromotive solution, we launched onto the market around 10 years ago now, and we wanted an electromotive valve solution that was as fast or even faster than the conventional pneumatic solutions, and as accurate or more accurate. And we actually ended up achieving both. The main thing, though, is that it's flexible. You have absolutely no air feed required. They use purely electricity to modulate and operate the valve directly. They're fast. They are the most dynamic electromotive actuator in its class. So compared to our competition, some of which their travel speed or their time to operate from close to open or vice versa can be measured in minutes, we can measure ours in single-digit seconds. Very, very fast. It's safe. We have an integrated battery or capacitor storage solution, which is programmable. So you can actually program what the fail-safe position is. It's robust, again, like the pneumatic solution, IP65 or 67, and constructed out of materials with high chemical resistance. Now, because we don't have the air to over-pressurize the electronic side of things, we wouldn't be recommending that you run them fully immersed, not that we would with the full pneumatic solution anyway. But they have just the same high levels of ingress protection that our pneumatic valves do. They're very smart. We have, when you see that we do the live demonstration, I will show a quick example of some of the diagnostic functions that are available from this kind of technology. But most importantly, for a modulating control valve, it has to be precise. And these are actually the solution now that we would go to as default for the most demanding control applications. And we'll show this when we look at the live demonstration of both. A quick look at the core components of it. On the top, we have the same easy to use HMI module that we use across the entire Bürkert range of process control valves, but also things like our standalone controllers and instrumentation now. A 360-degree LED status indicator on the top. So again, you have 360-degree visibility of what position the valve is in, or any messages that it's trying to send, an error, for instance. What we call the safe POS, the energy pack that I'll go into in a bit more detail in a second, our closed design, ensuring the hygienicness and the cleanness of the valve, a mechanical valve position indicator on the front in case of power supply, so you can still see when that LED light at the top can't work. Still a mechanical indication of the position that the valve's in, and the valve interface that we can use this on the entire range of Bürkert process valves. So little bit of a closer look at the internals of it. We use a brushless DC motor with a cogging torque brake. What that means is that when the actuator is at rest, so doesn't see a change in the control signal to move to a different position, nothing within the valve itself, so it doesn't matter what pressure or what flow rates are going through the valve, it cannot move. The motor locks in position, and it doesn't need any current, doesn't consume any power to have that lock. It's the natural feature of that DC motor that locks the valve in position with no current draw when we don't require the valve to move. We use the same non-contact as position sensor that we do on our pneumatic valve range, wear-free, high resolution, and again enables us to offer these valves with incredibly long life cycle requirements. One of the key features is the angular ball bearing. These are aerospace grade, very low friction, very long lifetimes. And help give us the incredible accuracy that this valve is becoming known for. And we couple all of that to a planetary gear with a high gear ratio that again enables us to have the best positioning resolution possible. The electronics module fits down the back with the PCB stack and the I/O module if required, but more and more we're seeing these being used on digital communication. The safe POS, this pack of optional super capacitors, and these can be pre-programmed to move the valve to any position on power failure, be that opened, closed, or any position within the valve travel. And we warrant that energy pack for 8 years. Alongside the angular ball bearing, there is also an aerospace grade ball screw, again, very low friction, long lifetime, and both of those efficiencies help us save energy within the valve, alongside giving us this very, very high levels of accuracy. And again, as I've mentioned, the mechanical position indicator, if you do have a case where you have power failure on your plants, but want to see that the valve has moved to what position has been defined for the safe POS energy pack, you can still see that using the mechanical position indicator. Externally, it's a very clean design. It's been designed around the same philosophy as the Element solution to go into hygienic applications. And we supply the actuator with the valve as one unit, perfectly adapted to each other to be as clean as possible. We have EVG 1935 conformity for food and beverage plants and FDA approvals for pharmaceutical sites as well. And compared to the traditional kind of yoke mounted style that our competitors would use for mounting their Electromotive actuators, you can see the cleanliness advantages of the Bürkert solution. So now we're going to move to the live demonstration. I have on one side of me here, I have one of our pneumatic valves. I'm just going to end the presentation and bear with me because I just need to change the camera. And hopefully now you can see if I can get it without a reflection. Not clear, but the main part of it is going to be on the main screen. This is just to show you what is going on the display, and we actually have a valve that is working in the background. So the main part of it here is we are going to use our Bürkert communicator software tool. So this tool is freely downloadable off our website. Many of our latest generation products now use this as a commissioning or maintenance tool. And we have a range of different methods of connecting to our products, be it modulating control valves like what we're going to look at today, our instrumentation, our controllers, our water treatment system. All can be commissioned and maintained using this Bürkert tool, and we're going to briefly show you some of the features of it. So first of all, we're going to look at the positioner. So we click on the positioner down here. I'm linked to it digitally. So on the home page, we can see the position. At the moment, we're not asking it to do anything. So it's sat there at 0. In here, you can have things like the diagnostics, so the status of the valves over its time, histograms, maximum, minimum values, what it's seen, how long it's operated for, traveled path, number of direction changes, etc., etc., etc. But for today's purposes, what we're going to do is go into the maintenance tab, and we can run this in simulation mode. So this is normally something that we would do on site, making sure that the valve is working to within its correct parameters. And we have a mixed wave that we're going to send to it that will be a simulation of both square-edged control signals and sinusoidal waves. I don't know if the microphone's picking up, but I can hear now the valve is starting to move. So I'm going to go back to the home page. And on the home page, I'm going to choose the 2 values that we want to display on a graph, they call output, that is built into the configurator, so we can see what is going on. It's a little bit zoomed in at the moment. Let me get it on a scale that hopefully is clear for everybody to see. Hopefully a little bit from there. Right, and we will just zoom out a little bit there. There we go. Okay, apologies on that. Actually, we'll pause it there because that's actually given us a full waveform, both square-edged and sinusoidal, that we can actually now look at. So I am going to try to zoom in on the square edge waves, first of all. With me. Hopefully we can just about see them if I zoom in. There we go. So we are zoomed in quite closely here. We are looking at a scale of fully closed, so 0% open up to 6% open, so very, very zoomed in. The green line is the position, the control signal that we're sending to the valve. The blue line is the valve reporting its position back. On the square edge signals, although it's very small, so we went from 5% down to 3%, so a 2% movement, back up to 5%, and then down to fully closed. And you can see, we are achieving within 0.2%. Positional accuracy, a little bit better when we went up, a little bit of a step hysteresis there as it adjusted its setting. But you can see on all of them, we have a little bit of an offset occurring, a little bit of a delay. And then if we zoom back out again, we can see as we went to fully open, try and get it all on the screen. It's up here somewhere. There we go. But we can actually see the speed of operation here. So we sent a signal for the valve to go to 55% open, which went from fully closed. And we sent that signal to the valve at 40 seconds. And then the valve had achieved that by 42, 43. So about 3 seconds to achieve a 55% opening time. We then sent a brief fully closed signal, so the valve tried to respond, but then almost immediately we sent a signal to try and go into the sinusoidal waveform, and we follow it very, very accurately. There is a little bit of an offset, we would expect that. Just try and zoom in a little bit closer on that. There we go. But you could see as we started to reach the top of that sinusoidal curve, this is where modulating control valves really start to struggle, especially pneumatic ones, where the hysteresis, the small amount of friction that we do have, the infinitesimally small amount that we're trying to change it. I mean, that hysteresis, we start to see it about when the valve is 96, 97% open. We're trying to go to 100% open. So all of this hysteresis is taking place within about 2 to 3 degrees of movement. But again, a constant change. Unlike the square edge signals, this is a constant change. And you could see the valve started to struggle a little bit. But again, keep in mind for this kind of control, this is extreme. And we have one of the market leaders in terms of accuracy and performance. But even then, you can see that slight offset, that slight hysteresis that we have at that point with the pneumatic control valve. So I'm going to stop that valve from whirring away next to me. Switch that off. It goes quiet. And now I am going to move over. Now this valve, the Electromotive one, bear with me a second. Maybe I can get it in shot. There we go. Not the clearest, sorry. Let me try moving it back a bit. Hopefully it'll come a little bit more in focus. It is trying to focus on our wall behind. So now I'm going to go to the EVA valve. Again, same kind of dashboard, same kind of functionality and diagnostics in here that we can see exactly the status of number of direction changes, how far it's moved, how long it's been in operation for, dwell times, everything that you could want to know diagnostically. But again, we are going to put it into its simulation mode. So if we go into maintenance, set the simulation, and we are going to generate again a mixed waveform. And now the Electromotive valve, and hopefully on the picture there next on the main presentation, you can start to see the plug of that modulating control valve moving up and down as it's responding to the control signal. I'm going to clear the data from our pneumatic valve, and I'm going to now choose the data from our EVA valve instead. Let me change that to green, so I've got red and green this time. So very, very similar to what we had with the pneumatic valve. Let me try and get it all on the same screen. There we go. Just as we're talking, it's just done a simulation of going fully closed to fully open. So I'll quickly just pause it there. So we can see that we actually sent that control signal at 28 seconds. And the valve, that was the valve was fully closed when we got the control signal, and 5 seconds later this valve was fully open. So obviously we can't have an instantaneous response, but it's very, very fast. I'll start this running again just so we can get some more of the displays. So it's now running the sinusoidal waveform. I'll let it complete a complete waveform as I'm talking, but hopefully you can already see the way it's following that sinusoidal control signal. You can see we get a little bit of jitter at the top, but significantly better than the pneumatic valve. Once I've got a complete waveform with some square edges as well, I will stop this and we can zoom in and have a little bit of a closer look. On the EVA valve, we tend to let the sinusoidal curves run for a little bit longer on the simulation mode. Just a couple of different ones to really show off this technology. But there we go, we're starting to get some of the square edged curves as well. And once it's generated a couple of those, I will stop it and we can zoom in and have a closer look. There we go, that will do us for now. So let's have a closer look at that sinusoidal curve, first of all. Again, we still see a very small amount of offset, but we would expect that from any modulating control valve. But you can now see at that top point, which is Why is that gone like that? Best laid plans. I'm not quite sure why the line has gone so thick. Apologies. This is more the software than what I'm doing. I might have to wait for it to do another. But again, you can see at the very top there how smooth that control curve was. Best laid plans, it's all gone a bit wrong. Anyway, oh, there you go. It's working properly now. Let me just get there. So we've looked at the sinusoid. So it's a significant improvement over even our own pneumatic modulating control technology that is market leading. I'll just let it create these square edge curves, and then we'll have a look at the accuracy on hitting these square edged curves as well. And hopefully the display won't do something a bit silly this time. So if we zoom in on those ones now at the top, we can see that we are hitting those set points almost precisely with no offset. So we saw a small amount of offset and a little bit of hysteresis on these square edge curves on the pneumatic one, whereas the Electromotive EVA technology is hitting precisely the control curves. So a marked difference actually, in a market leading pneumatic control valve compared to Bürkert EVA technology. So I will end the live demonstration there, switch the simulation mode back off again, and we will go back to my presentation. One way around. And so just change the cameras over again. So hopefully you're looking at me and not about for the rest of the time. Now, just in case we had a problem with the live demonstration, we did take some screenshots of an earlier test, but basically exactly what we've just seen. And this would be the expected behavior. So our element pneumatic valve solution, dynamic and precise behavior, some small overshoots for those small signal changes, small plateaus. So the plateaus when we reach the top and the bottom of the sinusoidal curves are all to be expected from a pneumatic valve technology. As good as we can make it, we still do see these slight areas where the hysteresis occurs. But we compare that to what we've seen with the EVA valve, where we have almost no overshoot or no overshoot at all, just as dynamic, if not more dynamic, so faster moving than the pneumatic solution, very, very precise, the highest resolution, and you can see on these screen grabs, now zoomed out, almost, very, very, and certainly in any kind of process control application, it would be very, very hard to detect even that change, those small amounts of hysteresis from the pneumatic system, but the Electromotive system removes them completely. Far and away the fastest, most accurate valve, modulating control valve currently available on the market. So our next step, we're going to have a look at the two Bürkert technologies head to head. So element versus the EVA one. So first of all, both actuator technologies are available on the entire range of Bürkert's standard linear process valves. So that's the angle seats, such as this, the globe valves, and our hygienic diaphragm valves. In terms of KVS values, we have everything from 0.1 meters cubed per hour up to 140. That would be for the globe valve range. The diaphragm valve range and the angle seat valve ranges are slightly more limited. Theoretical rangeability is a maximum of 50 to 1. At the smaller end, typically it's either 20 or 30 to 1, but that gives you an indication of, so the KVS is the maximum flow rates we can typically go up to. The rangeability would then be how low we can go from those maximums. In terms of seat diameters, we have everything from a 3 to 100 millimeter. Again, that would be with the globe valve range, where we have the widest range of options. Angle seat valves, typically ½ inch, 15 millimeter up to 65 millimeter. The diaphragm valve range, 8 millimeter up to 100 millimeter. Connection sizes, that's DN10, 3/8 of an inch, up to 100 millimeter or 4 inch. And we have a range of different actuators in both the pneumatic elements option or the EVA option. So for the element, we have a small diameter 50 millimeter valve solution, which is here. There are limited positioner and control head options available with those, and typically we can't provide those with a display. The 70, 90 and 130 millimeter diameter actuators would be the standard offering, and we do now have a full large diameter 225 millimeter actuator, which is actually also a full stainless steel construction rather than the plastic of the 50 to 130s with the stainless steel sleeve. The 225 millimeter is a full stainless steel actuator. The Electromotive, we have two different sizes of actuators, the AG2 and the AG3, and then each size has two different forces available. So everything from 1300 Newton meters for in the AG2 all the way up to 10,000 Newton meters in the AG3. In terms of operating pressures, both the pneumatic and the Electromotive solutions can cope with anywhere from atmospheric to 25 bar G. We can, on request, go up to 40 bar G with both ranges, but we have to look at the actuators that we're going to use and some other options to enable that. We can also go down to vacuum minus 0.9 bar G. Again, we would have to select some particular options to enable that. In terms of line connections for the valves, we cover all the major standards for flanges, threads, welds and clamp ends. In terms of media, gases, water, alcohols, oils, fuels, hydraulics, chemicals, steam, pretty much anything that you want to put through these, we have a solution to cope with. The medium temperature for both is exactly the same, minus 40 degrees C all the way up to 230 degrees C. We do have a cryogenic option as well, which takes that low temperature down even further. As far as I'm aware, we have only offered that on the pneumatic solution, although as far as I'm aware, there's no reason why we couldn't also offer that on the EVA solution as well. Ambient temperatures. So this is now dependent on what kind of positioner technology that you put on the pneumatic solution. With a remote positioner, we can go from -10 to +80 degrees C. With a direct mount, what we call the top control positioner, such as in the pictures here, that would be -10 to 55 degrees C. So the EVA actually wins in this regard. It can go as standard down to a lower ambient temperature of -25, and with a coupled positioner technology, which all of them have, up to a maximum of 65 degrees centigrade. Now, voltage supply, I was going to put NA for the pneumatic ones, but of course you can only really use a pneumatic modulating control valve with a positioner. All of Bürkert's positioners are electronic, so we know they need a voltage supply. For both technologies, we would need a 24 volts DC voltage, but we can tolerate a 10% tolerance on either of those. In terms of power consumption, again, the pneumatic solution will consume a bit of power, but it's a maximum of 5 watts, depending on things like whether you have a display or not, the technology options, the solenoids that are in there. The EVA range, the AG2 consumes 72 watts when the valve is removing. Remember that we have this cogging torque brake, so when the valve is not required to move, it consumes very little power, or no power actually, just the standby power, which is mostly for the display and high visibility LED. The AG3 would consume 120 watts when it's operating. Standby power, again, depends on the options, whether or not you have the display, the super capacity, safe POS pack, but between 2 and 5 watts. Pilot air pressure, this is definitely one we've put an NA for the electromotive valve solution. Typically on the element range, anywhere between about 5.5 and a 7 bar G of pilot air supply. The next thing we're going to look at is the dead bands. So this is what we would define the accuracy of these valves to be. So they have a default setting that they come from the factory with. The positioners on the element valves, the default is plus or minus 1%. So when the valve gets within 1% of its control signal, it won't move any further. It's to stop the valve hunting, constantly moving and causing wearing through its life cycles, although we have an industry leading figure on that as well. But that can be reduced using that Bürkert communicator software that I've already shown, down to plus or minus 0.5%. But the EVA, its default setting from the factory is 0.5%. But again, that can be reduced using the communicator software down to plus or minus 0.1%. Travel speeds is very hard to quantify on the pneumatic valves. The pneumatic valves are more dictated by the air supply pressure that you've got, the actuator size, but also the process pressure and the velocity of the fluid that you've got going through the valve that is all operating on the valve itself. So over here, we have actually given you the airflow rates of our two different positioner technologies. So we have low air capacity positioners for the smaller valves, typically 7 litres per minute of pilot airflow, or the high capacity positioners, which are up to 130 litres per minute. On the EVA, it's much easier because of the cogging torque brake. They don't move even independently of process pressure. So we do have defined. So the fastest one we have is 6 millimeters per second for the AG2 at 1300 Newton meters, 4 millimeters per second for the more powerful one, or 3 millimeters per second for the larger AG3s. And that all equates to, so we normally expect, so one of the things that when you come to Bürkert for a pneumatic modulating control valve is we would select the positioner for both the valve and the application. And we're normally looking for a response time of around 4 seconds. So that's fully close to open or vice versa. Again, with the electromotive valves, it's a lot easier to measure. The AG2 on the smaller sizes, it can be as low as 3.3 seconds, but up to 6.6 on the bigger valves. And for the AG3, anywhere between 8.7 and 12. But again, compared to some of our electromotive competitors, which are measured in minutes, incredibly low travel times. And again, that kind of accuracy that we have just seen with the live demonstration. In terms of expected life cycles, this again is very application dependent, but on the pneumatic solution, we would expect a customer to be able to achieve up to 7 million cycles using a full element solution valve. We've actually just had a customer who returned our valves for an inspection, and it was found that when we hooked it up to the communicator software and checked the life cycles, that over the last 20 years it had actually done 170 million cycles, which is extreme. But the customer's comment to us was, for 20 years, they haven't had to even look at the valve, bar some basic maintenance of the valve body, replacing seats, seals and stem packs. Other than that, it's just worked. So obviously they have replaced it like for like with another Bürkert element valve. But the EVA technology has moved that on even further. So expected lifetime now, using all the high grade materials that we have, the ball screw and the angular bearing, of up to 10 million cycles. In terms of inputs and outputs on analogs, so both have the ability to have one analog input and one analog output. Those are both configurable, so you can have a milliamp or a voltage input or output. The digital, although this is digital analog, so a transistor input and output for switching points or triggering the valve to do something. And with the process controller options that are available on both, you can have a direct sensor connection. So either 4 to 20 milliamp from a transmitter, frequency from something like a flow meter, or a direct PT100 resistance thermometer connection directly into the heads and have the valves control your process directly. But more and more common now is the digital communication. Both valves were designed to be operable over Bürkert's systems bus, the BOOS solution, which is based on CANopen. So both have that natively. And this is one area where the pneumatic solution still wins. So both we have the Ethernet field bus communication. So Ethernet IP, Profinet, Modbus TCP available on both. But the pneumatic solution, we can also still do Profibus DP. And with the pneumatics, we can do the sub-field bus networks of RZ and IO-Link. All of our technology now has the Bürkert service bus service interface. So that's what I was using for the live demonstration. So we have a tool which enables you to connect all kinds of different Bürkert technology up to a laptop, run the Bürkert communicator tool, and be able to commission, calibrate, and maintain the products directly from there. In terms of approvals, again, this is one area where the pneumatic valve still wins out. So our pneumatics for ATEX, it's a category 2 device suitable for ATEX zones 1 and 21, whereas the EVA is category 3 and can only do ATEX zones 2 and 22. But both are UL listed. Both have FDA approvals available, and both have EC 1935 conformity for food and beverage applications. There are also a range of oxygen, hydrogen, and water treatment industry approvals available for both valves to whatever is required within those industries. Major options. So on the pneumatic side of things, it's normally defining the function, the fail safety function ahead of time. So whether they're normally closed, normally open, or double acting. With the EVA valve, the option is whether or not you have that safe pos capacitor pack installed or not, and then that allows you to program whether you want the valve to be normally closed, normally open, or go to a predefined position, including just saying where it is on power failure. And both are available with or without display modules. More and more common now, certainly for networked valve solutions, to have them without the display module. And using tools like the Bürkert communicator tool, again, you can connect to one valve that has been networked to all of its others, and you can commission, maintain all of the valves from one point on the field bus network, which makes it incredibly easy to achieve, and you don't have to go from valve to valve in your network. The final thing we're just going to have a look at is an example of the costs of operation of 3 different solutions. So the standard solution here would be one of our competitors' pneumatic solutions. The Bürkert pneumatic solution in Element and the Bürkert solution in the Electromotive actuator EVA. We have to define some framework conditions. Being a German company, this has all been done in euros, I'm afraid, but it should give you a good comparison. But the frameworks that we have set is electricity costs at 30 cents per kilowatt hour, compressed air costs, so how much it costs to produce the compressed air that you're going to run the valves off, at 10 cents per meter cubed, and a current consumption of creating that compressed air of 0.35 kilowatt hours per meter cubed of compressed air created. We're going to work on a system availability of 100%. Time interval of 10 years and 100,000 cycles per year. So when we compare the three different solutions and how much air that they consume. So because at Bürkert, with our pneumatic solution, we use our in-house solenoid valve technology, it means that when our element valves aren't required to move, so they have a steady control signal, we consume no pneumatic air. Whereas our competitors, who still often use either inferior solenoid technology or even some still on flap and nozzle technology, you have a constant air bleed across those valves, even when they're at rest or on standby. The EVA solution, obviously, we consume no air at all. When obviously the valve is moving, even the element valve has to consume some air. Although with these figures, like for like, I would expect the Bürkert element solution to consume, because we use a piston design against a typical diaphragm actuator, I would expect the Bürkert solution to consume less air. But we will go with these figures as that's what I've got. So when we look at that over the lifetimes of the valves, it starts to really stack up how much air these, certainly our competitors use versus our element, and obviously the EVA using no air at all. Power, now these figures I slightly disagree with. The EVA solution obviously consumes electricity on standby because of the cogging torque brake, very little, but when it's moving we've put an average of 80 watts, so in between the AG2 and AG3. But both the Bürkert element solution and our competitor's solution would actually consume power. Typically, in this day and age, you are using electromotive positioners. Bürkert can only supply electromotive positioners, and both on standby and when they are moving, they will consume a low amount of power. Again, the Bürkert solution, it's between 2 and 5 watts for both standby and duty. And I would expect our competitors to be roughly similar. But I'll come to that with the cost, because we can actually add the standby cost, which is roughly the same of the EVA solution, to what we end up with at the total. So you can now start to see the amount of energy that we need to operate these kind of solutions. Our element solution, we would expect to be a quarter of the equivalent competitor's pneumatic solution, and the EVA solution nearly a third of the even what the element does. So when we look at that in terms of costs, we have our competitor's solution over 10 years at nearly 1,200 euros, Bürkert's element solution at 300, the EVA valve at 112. But I would be tempted to, on both the pneumatic solutions, to add that 105 euro standby costs. But it actually makes the argument for the electromotive solution even more strong, because that would put us at close to 1,300 euros operating costs alone, just for our competitor's solution, at about 400 for the Bürkert element solution, whereas the EVA would still be down at 112. So a quarter nearly of the operating costs for the EVA solution versus Bürkert's element solution over the lifetime of the valve. But these aren't the only costs. These are just the costs of actually operating the valves. And on the top of my summary page here now, getting to the end of our webinar this morning, I've put, another thing to take into account are that compressed air systems are expensive to install and maintain. Alongside those operation costs of just the valves, you have air compressors, you have distribution networks, you have filter regulator sets, everything that goes along. The leaks from distribution, for instance, all add up. Compressed air systems are very, very expensive to run. It's become more and more common these days for end users to rent air compressors from the manufacturers, and those manufacturers charge per meter cubed of air that is used. So having technology that doesn't use any air at all or minimal air is a huge cost saving. But in summary, so we would look to be using EVA technology in turnkey projects, so ground up projects where you can completely eliminate the requirement for having compressed air, even when you need dynamic control of the valves, which used to be a case that electromotive valves couldn't do. They were just too slow to operate. We now have a valve that can operate as fast, if not faster, than most pneumatic valves out there on the market. And by doing that, looking at the cost savings, both of the valve itself and the entire compressed air systems, you can start to see significant lifetime savings. The pneumatic valves, the Element range, are still where there's already existing air on site, are still a major upgrade for existing plant operations. The EVA technology, though, offers our highest levels of accuracy with speeds similar to pneumatic technology. So there is no downside in either speed or accuracy by going to the EVA solution. But another thing just to keep in mind that we haven't discussed today is another cost saving is ensuring that things like the valves are sized correctly. And use of welded valves rather than things like flanged valves in industrial applications. Bürkert's valves can all be maintained, the valve bodies, from the top. So seats, seals and stems can all be maintained, even with the valve body remaining in line. And those flanges both add cost to the valve, as well as lead to performance decreases of an application. They act as huge heat sinks, especially if they're not insulated properly. And finally, I would say, please, talk to us. Talk to us about finding the best solution for your application, be that Element, be that EVA, be that another product in our range. We always love to talk to people, find out what your frustrations are, what you're looking to achieve, and specifying the right technology for the job. So we're out of time this morning. I appreciate you all listening to my presentation. Should you have any questions, please feel free to ask them in the Q&A session now. But in terms of the recording, thank you very much for attending. I hope you've got something for today, and we really look forward to talking to you in the future about both your modulating control valve applications and any other applications that Bürkert might be able to assist you with. But on that note, I bid you farewell and good day. Goodbye.